Okay. So can you see my screen?
I can see your screen, kind of like an iPad type screen.
Yeah.
Yep.
All right. So thank you for the invitation, and it's quite good because this is like this sort of forced me to finish the paper. Um, it's very useful to give this talk for me as well. But I hope that is something that you'll find useful here as well. Okay, so the idea is to uh, try to derive I mean, there's a lot of models of epidemic spread on things like on networks. There's a lot of work on epidemic on networks. Here I want to sort of concentrate on the simplest non-trivial network, which is kind of like a grid, okay, in 2 dimensions, or a line in 1 dimension. So let's just review the basic SIR model. So susceptible, infected, and recovered. I think everybody here is familiar with this. So the idea is when susceptibles interact with the infected at some rate beta, the susceptibles become infected. So hence there's a minus. They go from the susceptible class into the infected class with a plus over here, the same term. And then this term minus gamma I, that's basically the recovery of the individuals. They recover with some rate gamma. When they recover, they go into the recovered class R. And this is like the simplest model. You can, of course, complicate it. You can add terms such as, like, you can go from the recovery back into the susceptible class. Like, so you can have, all sorts of other terms. So you can have minus mu R plus mu R if with time you lose immunity and stuff like that. And there's also, you can include asymptomatics. This is having free classes is the simplest model, but in the context of coronavirus, there's been models with many, many more classes, but the most important probably being asymptomatic individuals, as well as hospitalized and stuff like that. Here, we consider infected and asymptomatics as basically the same. Anyway, and this is more general than just for COVID. It's for any kind of epidemic disease. Okay, and this is the typical typical graph that one gets, where you have an infection starting with very low numbers, growing exponentially at the beginning, then eventually, at the same time as the susceptible class goes down in numbers, then eventually it sort of saturates at some point. And then because of this gamma term, minus gamma I, it goes back down to zero. So that's the typical progression of this model, epidemic, using this model. Okay. So one thing to point out is that oh, sorry, so just said, everybody can hear me, correct?
Yep, we can hear you just
Okay,
fine. Yeah.
all right, sorry. Okay, so one thing to point out is that at the onset of the outbreak, when at the onset of the outbreak, the infections and the number of infected is very small, and so then if I can just assume that if I can just replace this s here by just the initial value of s as 0, then I get just basically growth linear growth model for the number of infected. Okay, and then this quantity is in parameter in brackets, beta s0 minus gamma. If it's negative, so if gamma is sufficiently large compared to the population size, then the disease doesn't progress, it actually decays. But if it's positive, that's when you have the outbreak. So it's kind of a stability condition where this term in brackets is 0, and it's often written in this way here. So in other words, this beta S0 over gamma, that's often denoted by the reproduction number R0. If the R0 is bigger than 1, then you have an outbreak. Okay, so now what I want to do is I want to incorporate sort of spatial component to this model. I mean, already there is some sort of notion of space here because the way I've written this SIR model, like there is this S, this susceptible number susceptible can be thought of as being a function of space. So just that already gives us some information. And if you think of it that way, then actually R0 here already has spatial information. This R0 production number depends, and in fact is scales linearly with the number of susceptibles S0. But yeah, we want to see what's the effect of sort of the movement of the population on how can we incorporate the motion of the population. Okay, so one simple way to attempt to do this, and this, I think there's a number of papers that kind of do this sort of thing, where they take like the basic SIR model, and then they introduce diffusion for each one of the components, right? So they introduce this diffusion terms here. Okay, so that's one way to do it. Now, but there's an issue with this. It's not really justified in this following sense. Okay, this assumes essentially, like even if you just look at the first equation for the susceptibles, like so ST is equal to SXX. Okay, so that's kind of assumes that people are diffusing, right? So if you start with some non-homogeneous population distribution, such as like a city and a rural area, then if all you have is diffusion, then eventually the population density will like homogenize, and everybody will have like basically everybody. So then you're not going to have cities anymore. Everybody will just diffuse, and until you have a constant density everywhere, right? That doesn't happen in real life. That's not actually what happens. Okay. What actually happens is that the way we want to try to incorporate this spatial movement is that what happens is that people go to work, okay, and then maybe they get infected when they go to work, but then they return, they come back to where they came from, right? So they don't just diffuse or do the random motion. They actually go somewhere, potentially get infected, then they come back to where they came from, okay? So that's very different from a diffusion. So that's why, like this is not really, at least I don't think this is an appropriate model. Okay, so so how are we going to model this sort of idea of going somewhere and get infected and then come back home? Okay, so that's the key thing. So what we're going to do is we're going to discretize first. To start with, I'm going to take a space, okay, and discretize it into bins. Okay, so let's just say in one dimensions. They can do the same thing in 2D, and in each bin you'll have some population, like so. Susceptibles. So the number of susceptibles in each bin will be denoted by like S1, S2, S3, S4, etc. And the same thing for infected and so on, right? Okay. All right. And so then what we're going to model is the simplest model is to assume that this susceptibles travel to the adjacent bin. Okay, so now in reality, and this can also be modeled, they can travel not just to the adjacent, but like further away. But let's just look at the simplest setup. What happens if we assume that everybody just travels just to the adjacent bin? Okay. And furthermore, again, here to simplify things, I'm going to assume that only susceptibles move, infected don't move. Later on, we'll talk about also how to incorporate the movement of infected individuals, which we'll need to do. But let's, for simplicity, just assume that only susceptibles move around. Okay. And so then what we're going to do is I'm going to define this quantity delta ij, which is the number of new infected, per day. Okay. And so I'm going to write down an equation of what it looks like. Okay. So here, let me just write this down. So I have some infection rate beta. And so when infected individuals interact with susceptibles, that's going to contribute to my infection. Now, infected individuals inside my my bin J. So I have, let me do this. So I have the bin J, I have bin J plus 1, and I have bin J minus 1. Okay. And so so what happens? This ij is the number of new infected in the bin J. Okay. So this is what's going to happen. So I'm going to write, this is good. I'm going to put Sj in here, but then minus 2 times alpha times Sj. And I'll explain this in a minute, what this 2 alpha is. That's going to be, this 2 alpha is going to be just the number of individuals that travel away from, so alpha is going to be the rate of travel, okay? So some individuals stay at home, some individuals go to work. And then I'm going to say plus beta, and then I j minus 1 times alpha times S j. Okay, and then plus beta I j plus 1 alpha S j. Okay. So now let me explain, and feel free to interrupt to ask questions if something is not clear. So this term here is the daily infection. So this is daily infection of Sj inside the bin J. Okay, and this term here is the daily infection of Sj inside the bin J minus 1. So this alpha here is the travel rate. So some rate of individuals, namely this alpha times Sj, so that's some fraction of individuals travel to the neighboring bin J minus 1, and then they can get infected there with some rate beta. This rate here is the same as this beta here. Okay. Those individuals that travel to the bin J minus 1 are subtracted from the current individuals that are staying at home, right? So it's like some are staying at home, some are going to work. Okay. So that term is, so yeah. So I don't know how to do the arrows here, but basically it's like there's some individuals that travel, and that rate is us times Sj. And then after they travel, they become infected with the rate beta ij minus 1 with this rate, right? And all of that happens in the same day, okay, or in the same time interval delta t. Okay, and then this is the same thing except travel to bin J plus 1. Okay, so some travel to bin J minus 1 with the rate alpha, and some with the rate alpha travel to bin J plus 1. Okay, is that clear? Okay, so, and that's the key thing. And now the model then becomes simply that ij, the number of infected individuals at time t+1, the following day, is the number that are currently infected plus the new number of infecteds, that quantity there, okay? And for Sj, you start with whatever was before and then minus delta I. Okay. So that's the full model, okay? This equation plus those two equations. And that's the full the full model in like that incorporates space. And now, okay, I just wrote this down again. Now let's look at the continuum limit of this model. So if I look at this equation delta ij, I'm going to rewrite this. So beta sj I can factor out for all of those terms. And what I'm left with is inside is this stuff here. Okay. So now I do, and here this probably looks very familiar to most of you. This is like a Laplacian. So this I can write this. Okay, so beta s, and then so here I'm going to have ij as abbreviated to I, and then minus 2. No, sorry. So plus alpha times. So let me write this again. I j minus 1 plus I j plus 1 minus 2 ij. And this is nothing but like the discretization of the second derivative operator, okay? So that would be I of x. That would be just I. That's just this. Yeah. Divided by, yeah, that's just that. That's what this is. Okay. Approximated as delta. So delta x here is the spacing of the bin spacing. So this distance here is delta x. It's kind of the distance from one bin to another bin. Okay. So now, and then I have I of t plus 1. I can approximate this by I of t, right, ij of t, plus, like, so delta t here is just 1, so plus delta t times ij prime of t, okay? And so now I have, so then the equation for I of t plus 1, like this cancels out with, right, so I have this is equal to ij plus delta ij. So this thing and that can cancel out, and I get it, derivative with respect to t, is equal to, I have beta s I, and then I have plus beta s delta x squared times ixx. Okay. So notice now that this s here, the number of susceptibles, enters into the diffusion coefficient. Okay. And the same thing I have for sst is equal to just minus those two terms. Okay. So this is what we get. This is the equation that we get after this manipulations. And here, again, yeah, well, I forgot the minus gamma here. So right, minus gamma I. So minus gamma. Okay, so so here's this is a state-dependent equation in a sense that S here depends on, so both S and I are functions of time, t, and space, x, okay? And we have this kind of a diffusion here, where the diffusion coefficient is depends on S of x. So it's sort of state-dependent diffusion. For S, the diffusion of S, there's actually a negative sign over here. So it's kind of a negative diffusion for susceptibles. So it's not at all like just throw in some diffusion terms and that's kind of the model. No. So really, so when you derive from first principles, this is what you get. Okay. Any questions so far? So good.
I guess
right.
your alpha just got redefined into that diffusion coefficient.
Oh, right. Yes. Thank you. So this here is what I call alpha.
Yeah.
Is a D. Oh, and then there's an alpha.
And you lost an alpha there too, but it's not a big deal.
Alpha there. Yeah. That's right. Yeah, that's right. So D here is this beta times alpha times delta x squared.
Right. So the difference between this and the naive ones, I guess, is just you multiplied the diffusion or the second derivative terms by the s, or you derived the
That's right. That's one difference, and the other even bigger difference is this is a minus sign.
Oh, the
rather
sign
than a plus.
difference, right? Yeah.
Yeah. So it's not at all like it's not at all diffusion. It's something else completely different. But it's kind of this involves this diffusion, but yeah. Okay.
Okay.
Yeah, so let's see. Let's just have a look at how this. And then the other thing is that like this model, as one expects, like just by adding s plus I, okay, and integrate, and then basically the diffusion disappears. So as one expects, this model kind of s plus I plus r, I must say, if you will also write the r down. And then this model actually conserves the population density, okay? So it doesn't actually diffuse anymore. Yeah, as it should. So whatever model you write down for this, whether, you can have much more complicated things than this, it should conserve population density at the end of the day. Like, so S plus I plus R must be constant in both time as well as space, right?
Well,
unless you have like huge movement of people.
Yeah, I guess you're demanding local conservation. Well, conservation of population density locally anyway. But I mean, you could just demand that the integrals be like just the total number of people, allow people to go from place to place. But I guess you're working under the assumption that doesn't really happen.
No, that's not like it's not like people suddenly move out of Halifax and everybody goes and live in Moncton.
Yeah, fair enough. Yeah, okay.
Yeah. Exactly. So it is important, I think, to have conservation of like locally, not just globally in space, but locally in space as well. And this model allows for that.
Well, it kind of depends on your time scales, I guess, because like if you're looking over the course of the day, then the amount of population in houses goes down and workplaces goes up. But anyway, I guess it depends on what time scale you're looking at.
Right. So at a time like, so the population density can change over years, right? Which is what if we're looking at like a much shorter time scale of the disease, the disease propagation tends to happen at a much shorter scale than like the general change of population.
Yeah, I was kind of thinking the other way. Over the course of a day, the population density tends to change a lot.
Okay, right.
People wake up.
Yeah, so this is kind of like a snapshot average over the entire day.
Yeah. That makes sense.
That's true. Yeah.
Okay, thank you.
Okay, great. So let's have a look at an example to see how this works. So here I just make up some function that's this S0 here, which looks like this. Okay, and then there is the gamma, and then I take beta equal to 1. So gamma is below this graph. So as long as it's below, then the disease is not being suppressed. Like at least initially the disease will spread. But I'm going to start with I'm going to introduce like just like one individual disease like at the left hand point. And here the other thing to notice, I guess, is that this diffusion d here is taken to be very, very small. So it's a kind of slow propagation. Okay. So, and here, let me show you what then happens. Okay. So here's time versus the disease starts to grow. And so this kind of a wave that propagates, because I introduced the disease on the left, but because this blue dash curve is above this green dash curve, the disease will still grow, but it slows down as it gets to this minimum here, but nonetheless continues to grow. As the population, as it goes to where there's high density of population, it speeds up. And then eventually it propagates throughout the whole domain until sort of, yeah, till everybody gets infected. So this is the picture here. The top one is S versus, so space versus time, and infected versus time. You see this pocket of infections happen here. Then for a while, like the infection is spread, and then there's sudden speed up of the disease until it propagates through the whole domain. Okay. I can now increase this. Let me just speed up the simulation. Let me increase the gamma so that recovery is faster. If I increase the gamma, recovery is faster. I also increase the simulation speed. Again, it's kind of stuck in here, but then eventually it propagates, and suddenly it even sort of it exhibits some kind of a super diffusive almost behavior where it kind of jumps. The wave doesn't just continuously go from left to right, but it can actually jump. Okay. All right. So that's how this. So that's what the simulations of this model look like. Let me talk about the stability. Okay. So if we look at the start of the epidemic, where infection is very small, then we can just replace at the start. Let's just assume that the susceptibles don't change very much. Okay, that's what happens at the start. So when only a small fraction of the population gets infected, and then this model, you can kind of linearize it, and you get this. So basically, you replace S by S0, and that's what you get for the infected individuals. And this is now a linear model. And now we can look at the stability of this model. So just like we did for, at the beginning, I wrote down the stability for just an ODE model for SIR. If you look at just the SIR, you just look at this, and then the stability is just controlled by the sign of the fin in the brackets, right? But here we have a fully spatial PDE problem. So stability will also be dependent on the diffusion term. And so how do we take that into account? In other words, what we want to compute is some kind of measure of R0 for the entire population, not just like locally. Right? So we do the usual thing. We linearize in time and space. So we'll look at the solution of the form e to the lambda t times some phi of x. And we get this here, an eigenvalue problem to solve for lambda. Right now, this is like an ODE eigenvalue problem. So if there was no diffusion, if this term wasn't there, right, then you just have like the usual stability for the SIR, the ODE SIR model. But now we have, the question is, how does this change stability when you have this diffusion term? Okay. And let's just, we need some boundary condition. We need to impose some boundary conditions in order to solve this, in order for this to be well defined. And I'll just take the simplest boundary conditions, no flux, Neumann boundary conditions. So you have some interval from 0 to L, right? And you have no flux. So nothing gets in, nothing gets out.
Were those the boundary conditions you took for your simulations as well?
Yeah, that. I actually took that for my simulations.
Okay, thanks.
You need some kind of boundary conditions, otherwise it's like in order for the problem to be. The other simple one you can take is just periodic boundary conditions. The results are very similar for that. Okay, so that's where we start. And now, in general, this is like to solve. This is like an ODE eigenvalue problem, and S0 of x is sort of completely like it's prescribed. It's arbitrary. So there is no like explicit solution for general S0 of x for this problem. Second order ODE. Okay, but there are certain limits that we can do. In particular, the limit, well, one obvious thing to do is like if S0 of x is just independent of x, so it's just constant. So for a constant population density, then that's a simple problem. And then the leading eigenvalue is just beta S0 minus alpha. It's just this term here. Okay. And that coincides with just stability of the ODE itself. The other interesting, the other interesting limit is what happens when d is equal to 0. When d is equal to 0 here, you kind of get the same thing, but now this lambda depends on S0, and that depends on x. So you have, for each point in x, you have a different growth rate, and then the stability is to say that growth everywhere is negative. So in other words, you replace this, you look at the maximum of S0. So that gives you the sort of the notion of the reproduction number R0. For inhomogeneous space, you would have beta times the maximum F0 divided by gamma. Okay, and now let's see what happens when d is small. When d is small, then to leading order, the threshold is the same as when d is equal to 0, but then there's a correction term that comes from d, and this can be computed using sort of Hermite polynomials. You get a Hermite ODE, and then look at the first eigenvalue of it, and then basically you have this correction for small d. The maximum, this S maximum called prime, is the maximum of S, but shifted downwards by this factor that's of order of d to the 1/2. Okay, that's the result. And then the other limit that can be done explicitly is the limit of large diffusion. So when everybody moves very fast, okay, in that case, rather than having maximum of S, you look, or the average of S if the S was just constant, you end up looking at the harmonic average. It turns out that then the R0 is beta over gamma times the harmonic average of S. So the harmonic average is 1 over the integral of 1 over S. Okay. So that's what the harmonic. So that's the interesting thing is. So for example, if I have like a function like this, right, then I have the maximum is 1.5. The harmonic average is 0.866. So the maximum is what we need for like d is equal to 0 or small. Okay. This limit is d is like going to infinity, a very large d. And then if you look at the average, you might think that if like a diffusion is very large, then naively you might say, well, then the whole population, we just can average over all the imperfections. Like if we just take the average over the entire population, and we can use that in our computation of the reproduction number. Okay, well, it turns out that the average is different than the harmonic average, right? So the harmonic average actually is a better measure of the entire population for the purposes of the reproduction number. Okay. The other conclusion is that in the limit where d is very large, okay, if you have heterogeneity, then it's actually well known that the harmonic average is always less than the standard, like the mean of the population, or the average density as mean, right? So that means that if you have very heterogeneous population, in the limit of very large diffusion, that heterogeneity can help to suppress the outbreak, because it brings down, R0 is essentially proportional to S somehow, right? So when you when you use the harmonic average rather than just the arithmetic mean, it brings down R0, okay? So very heterogeneous population can help to suppress the outbreak, okay? On the other hand, if there's very little movement, then instead of the average, you need to use S maximum. So then the outbreak will happen at the point of the maximum of the population, right? And the maximum of S is always bigger than the average of S, right? So in the limit where there's very little motion, heterogeneities actually help to initiate outbreak. Now, that's just, of course, in that case, the disease may not spread beyond the points where S has a maximum, okay? But nonetheless, that's the result. Okay, the other thing we can do is to measure the speed of the infection. So again, this is the linearized equation for just the initiation of the infection. When you have a wave propagating as in the simulation that I've just showed you, then at the front of the wave, there's very little infection. So actually, then this is where this equation is actually valid, where this linearization is valid. It's valid at the front of the wave. Okay, and then one can use sort of in the limit where d is very small, we can assume that we can use kind of adiabatic theory, which what basically that means is you just freeze the coefficients S0 of x, and because in the limit of d is small, it turns out that the front propagates very slowly, and assuming that we can just, and it's very sharp front as well. So locally, it's like saying that S0 of x is just constant, independent of x. So imagine this was just a constant, right? Locally, then one can use like sort of a Fisher-Kolmogorov equation, the minimum speed of propagation there, and one obtains this formula asymptotically. Right? Now, surprisingly, it actually works pretty well when you compare it with numerics, at least for some regimes. So here's an example of comparison where here I plot on the vertical axis the speed, which is slow for small d. I think I used the above example, versus the x. Okay, so speed initially is fast, then it slows down, then it speeds up again. Right? That's the example with the two humps kind of population density I use, and then it slows down again. Okay. But something very different can happen when and this is, in this case, this assumes that this quantity is positive everywhere, right? If you have areas where you have locally negative growth, then this is no longer valid and something else happens. Okay, let me show you this case here. So now let's do a simulation where I take gamma equal to, let's say, equal to 1. So here you can see the disease starts to propagate, the infection grows, okay? But then it reaches this point where in this region here, there's a negative growth rate. And so the infection kind of dies out. and it looks like this is like a buffer zone, and it stops the propagation call. Okay. So it looks like it's just died out and no more propagation. Nothing happens. See? Oh, wait a minute. What's going on in here? Suddenly, it reappears, the infection reappears at the maximum peak here after some time, right? And this area also gets infected. So at the end of the day, even though there's like a buffer zone between these two infectious areas, the disease kind of is able to sneak through this buffer zone. It is able to tunnel through onto the other side and reappears at the maximum of the population density. And then everything gets infected that can be, right? And then you get this steady state that looks like this. So this is kind of interesting that you have, even if you have sort of buffer zones, you still have everything that can be infected still gets infected.
But if
And yeah,
if S actually went to 0 in between those two zones, though, there wouldn't be any propagation, would there? S naught
if
went
S goes to 0 all the way to here, that's a good point.
Well, maybe not 0 local, like actually. Do you have some differentiability requirements on smoothness requirements on S naught here, or S0 or the?
I haven't thought about those kind of smoothness questions, but if you take, let's say S, if we assume that S is even small but positive, right? Here, the decay rate here of the disease is very large in this buffer zone, so it really doesn't propagate. And you can see actually in this minimum point, the dashed blue line is the initial population of susceptibles,
Yeah.
and at the end of the day, nobody gets infected in this buffer zone, right?
Yeah.
And yet, or almost nobody. Like there's actually like maybe 1 out of a million, let's say, gets infected, and that might be enough to sort of kick the disease and propagate it all the way to the other zone.
Yeah, which kind of makes sense. If the conditions exist for exponential growth, you just need a little bit to get to the other
Exactly.
side, right?
Yeah.
Yeah, I'm just actually wondering if you took S0 to be something like piecewise and you had a finite interval in which it was 0, then it shouldn't go
Yeah,
across that.
that's right. I assume that should stop at cold.
Yeah.
That's probably correct. That's probably true. Although I haven't tried this, but I would yeah,
It
that's
should
right.
work like that.
It should work.
Yeah.
Yeah. Okay. So finally, I want to sort of see how I want to show you how, like, the idea here. This is of course a very general model, and it's nothing to do, like nothing specific to COVID, right? Which is good in a sense to have general models, but it's bad because it doesn't actually explain like a specific situation. But however, phenomenologically, I think there are some things in this model that are useful. Okay, and as an example, I'll use Nova Scotia. So here is the graph of what happened in Nova Scotia. In terms of, we had like basically the first wave here, that's like May last year. Then you see a little bump over here, and that was about December, this past December, when there was actually a 2-week shutdown for restaurants and stuff. They still kept the schools going, but they shut down some schools. There was some infection, some local spread going on. And then finally, the really big spike is here, starting like early April. We had a huge spike, well, huge in relative terms. I mean, even like it's really not that big compared to most other jurisdictions, where at the height of the spike, I think the most that got infected was like 30 people at once. I don't know why it says maybe 100 at once, compared to and then it went down because there was very strict lockdown measures that were placed, and all the schools were closed from May until the spike died down. Okay. Anyway, so that's that. And so in particular, this last spike, what happened was, if you actually look at the data, is that almost all of the disease, almost all of the cases were centered around two centers, around Halifax, of course, and around Sydney. Now, Nova Scotia has, like, Sydney has 30,000 people. Halifax has about 500,000 in the surrounding area, right, HRM. And that's half of the province right there. And Sydney is actually the second biggest population center in Nova Scotia after Halifax. Okay. And so whether it's in the third wave or through the entire duration of the pandemic, Halifax had about 80% of all the cases in Nova Scotia. And Sydney had another about 10%. Another 10% were in Sydney. Okay. So, and then during the last wave, like, so basically more than 90% of it elsewhere. So this is the kind of lens. So this kind of is consistent with what we see in this model, where if you have two population centers separated by a buffer zone where there's almost no disease, you can still have sort of a spread of the disease from one population center to the other. Okay. Yeah. So this is the idea of this tunneling. Here's another example of this. I think that's just the example more or less that I show. So basically, these propagates, then you hit the buffer zone where it gets killed, but then still it reappears on the other side and propagates the other way. Yeah, and then you have two sort of spikes here, and then the other spike on the other side. All right, so I think that's all I wanted to say about this model, and yeah, and feel free to let's see if there's any more questions.
Hey, Theo, I'm actually still here just briefly, but I've got to run in 1 second. I'll be back in a moment. So I'll see if Amy's got any questions or anything.
Yeah, I was all set to go. I thought I was in charge. I was co-host.
Yeah, you are in charge. You are in charge.
I really like that, Theo. Like I like that you threw out the diffusion model.